Welcome to Lecture 25, in which we will continue to talk about sequential circuits. And in the first case that we'll consider today, we have this circuit, which, for the sake of saving space, has been broken up into two diagrams side by side here. We have two JK flip-flops here. The output of the first one, the outputs are A and A prime, and the outputs of the second JK flip-flop are B and B prime. And we'll call the inputs to the first JK flip-flop JA and KA. The inputs to the second JK flip-flop we'll call JB and KB. And you see what signals here determine the J's and K's. Our input, we have a single input, which is X. Down here, B, of course, refers to this, and A here refers to this. So you should imagine that there's a connection between this output and this input line to this AND gate. And likewise, from the output of this flip-flop here to this AND gate. And then for the output of our sequential circuit, as usual, that's called Z, and it is the output of this OR gate, which is ORing together the outputs of these three AND gates, and here are the inputs to the AND gates. So you should consider all of this as one sequential circuit with everything connected together in the appropriate fashion, but we've just broken it up into two figures for the sake of saving space. Now, you can probably see from the second part of the figure that Z, the present value of Z, does depend on the present value of X. Remember, Z is the output of the sequential circuit and X is the input. And so since the present value of the output depends on the present value of the input, this is a Mealy circuit. Remember in lecture 24, we looked at a Moore circuit. Well, this is a Mealy circuit. And I'll go ahead and skip down just a little bit. You remember, as with the Moore circuit that we looked at in the last lecture, the first thing we want to do is to look at the excitation and output equations, and if we skip directly to the output equation for this, you see that it is the OR of XB prime, XA, and X prime A prime B. So that's what we have right here. X is equal to XB prime, or XA, or X prime A prime B. And again, here is this equation makes very clear the present value of Z, the present value of the output, depends on the present value of the input X. So again, we have this arrow pointing here to this statement that this is a Mealy circuit because the present output is a function of the present input. Now for the excitation equations, you can clearly, the excitations to these flip-flops, as was mentioned already, JA and KA for this first flip-flop, and JB and KB for the second flip-flop. And you can see that JA is X ANDed with B, KA is simply X, JB is simply X, and KB is X ANDed with A. So these four equations are our excitation equations. And just as we did in the last lecture, you will recall we had D flip-flops there, and we assumed that they were positive edge triggered. Likewise, in this lecture, we will assume that the JK flip-flops are positive edge triggered. Now, there's one more issue to discuss very briefly before we continue. If these JK flip-flops are positive edge triggered, then we have learned that that means that the values of A and A prime and B prime can only change immediately after the positive edge of a clock signal. Now we come over here and look at the diagram for Z, the output, and we see that it depends on A and A prime and B prime. But as we've just pointed out, it also depends on X and X prime, and unless we put some kind of restriction on X and X prime, it can change at any time. And therefore we have a situation here where Z could be changing when the state changes, or Z could be changing when the input changes. And so what we'll do to simplify this situation a little bit is we will assume that X changes, X is permitted to change only immediately before the positive edge of the clock. And this way, if X will change immediately before the positive edge of the clock, then that means that once the positive edge arises, then we'll have an X and an A, which and likewise here an X and a B, so we can compute JA and KB. And also, then once we have these excitation signals, we'll be able to compute the next values of A and B. So there will be a brief time there from the moment just before the positive edge to the clock until the moment just after the positive edge of the clock, when there will be, in some sense, you might say, an ambiguity, because notice that X will change immediately before the positive edge, and this will initiate a change in Z, but then immediately after the positive edge of the clock, then A and B can change, and this would initiate another possible change in Z. So we're not going to worry in the end when we give an input sequence of X's and determine what the output sequence of Z's will be. We will not worry about that brief moment when the clock has the positive edge, or from the moment before that when X is allowed to change to the moment after that when A and B will change. We don't worry about that very brief time while the clock is changing. We'll only want to look at other times and predict what Z is at these other times in response to a given X sequence. So now, having said all of that, we can proceed with our analysis. Again, here are our excitation and output equations. And just as we did the other day, after forming the excitation and output equations, we next want to form the excitation table. And so let's see what we can get. Here we have JA and KA for both x equals 0 and x equals 1, and JB and KB for both x equals 0 and x equals 1. And notice that here on the Mealy machine, since the output depends on X as well, we need to have the two columns here for the output Z. Okay, so let's see how this goes. Let's start with JA. JA, when X is equal to 0, as it is in this first column, the equation for JA reads JA is equal to 0 ANDed with B, and 0 ANDed with anything is 0. So in this first column, we can say 0, 0, 0, and 0 for JA. What about KA? Well, KA is equal to X, and in this column, X is equal to 0, so we also have 0, 0, 0, 0 there. So the X equals 0 column is very easy to analyze. What about when X is equal to 1? Well, when X is equal to 1, clearly since KA is equal to X, it will always be equal to 1 in this next column. So we have 1, 1, 1, and 1. And when x is equal to 1, we can see from this equation that JA will be equal to 1 ANDed with B, and 1 ANDed with B is B itself. So in this column we have that JA is equal to B. And so in the first row it's 0, and then 1, and then 0 and 1. So this is these are the values of JA and KA for all of the possible states and for all the possible inputs. And now we want to calculate JB and KB in those same situations. Okay, JB is equal to X, and so in this first column X is equal to 0, so we have 0, 0, 0, 0. And in fact, we might as well go ahead and fill in the second column as well, because then JB again is equal to X, which in the second column is 1. Now what about KB? Well, KB is equal to X ANDed with A, and so since X is 0, we have 0 for the values of KB in this column, and here in this second column, when X is equal to 1, 1 ANDed with A is A, so KB is equal to A, and therefore we have 0, 0, 1, 1. And now let's see about Z. When X is equal to 0, this term drops out, and likewise this term drops out. X prime will be equal to 1, and so we simply have A prime B. Again, when X is equal to 0, Z will be equal to A prime B. So that will give us 0 in this case, 0 in this case, 1 in this case, and 0 down here. Now, when X is equal to 1, this last term will be 0, because 1 complemented will be 0, and 0 ANDed with anything is 0. So when X is equal to 1, this will go away, and we'll simply have B prime or A. So B prime or A will give us a 1 here. B prime or A would give us a 0 here. B prime or A would give us 1 here, and B prime or A would give us a 1 there. And so this concludes the excitation table, and from this table we should be able to get all of the other information that we need for this problem. However, we do need to be very careful, because we need to remember just how the JK flip-flop works. So now this is left over from last time, so let me erase this. And of course, we don't need to put in the state names yet, because this is the transition table. Okay. So now let's look at this very carefully. In the X equals 0 column, we start out, let's look first of all at what's happening with A. Okay, A here in this first line, A is equal to 0. And in the X equals 0 column, in fact in every case in the X equals 0 column, we see that JA and KA are 0. So we have 0, 0, 0, 0, 0, 0, 0, 0. Now for a JK flip-flop, when J and K are both 0, the output doesn't change. In other words, the next value of A will be equal to the present value of A. So and this makes things very simple. We simply have 0, 0, 1, 1 in the X equals 0 column. And again, the reason for that is that in every case here, J and K are both 0, and when J and K are both 0, the next value of the output is equal to the present value of the input. Excuse me, the present value of the output. So that is A plus is equal to A. A is 0, 0, 1, 1, and therefore A plus is 0, 0, 1, 1. Okay, now what about B? Well, for x equals 0, JB and KB are also both 0 in every case. So B plus will also be equal to B in the x equals 0 column. So we have 0, 1, 0, 1, that's the value of B, and likewise then that will be the value of B plus, 0, 1, 0, 1. Now, I hope that you followed that and encourage you now to try, in fact, this next column is the most challenging one. I strongly encourage you to turn off the video now and to try to fill in this next column yourselves. And then once you have it done, resume with the video and see if you were able to do everything correctly. Okay, so I hope that you had luck with that, but let's now do it together and see how it goes. So now we're in the x equals 1 column. So that means we're looking here for the information about what's happening to A, and we're looking here for information about what's happening to B. So let's look first for A. Okay, A is 0 in this first line, and JK for that A flip-flop are 0 and 1. Now when J is 0 and K is 1, that tells you that the next value of the output will definitely be 0. It doesn't matter what the present value of the output is, the next value will be 0. So we have a 0 there for the next value of A. Let's now go to the next one. In the next line, A is again 0, but this time J and K for that flip-flop are 1, 1. And remember that when J and K are both 1, this is the toggle condition, so this 0 will become a 1. Now go to the next one. In the next line, A is 1, and we have JK is 0, 1. And remember, 0, 1 sets it equal to 0, regardless of what the present value of the output is. So we have 0. And then in the final line, A is equal to 1, but JK is 1, 1. That's the toggle condition, so that 1 will become a 0. Now let's look at what's happening with B. Now here's the present value of B, and then we need to look all the way over here at these numbers for the appropriate value of X. Well, for J and K for this value of X, let's say. So, okay, when B is equal to 0 and JK for that B flip-flop is 1, 0, well, when J is 1 and K is 0, that says that the next output will be 1 regardless of the present value of the output. So we get 1 here for the next value of B. And in fact, looking down, we can see that the next one is the same situation. J and K are 1, 0. So that will definitely say that the next value of the output B will be 1. Now, in the last two cases, J and K are 1, 1. So in both of these cases, we're going to want to toggle the output. Now, in the third line, B is equal to 0, and we have the toggle condition. So B equals 0, the next value of B will be 1, because it gets toggled. So we get 1 here. But in the last line, B is equal to 1, and when we toggle that, the next value of B will be 0. And of course, no extra work is required for the output for calculating Z. We just copy that down immediately. So we have 0, 1, 0, 0, and 1, 0, 1, 1. So I hope that that wasn't too terribly bad. And in fact, I'd say that if you got that all correct, you really are well along your way to understanding the analysis of sequential circuits. And so now we want to draw the state table, and we'll go ahead just as we did before and now label the states, and we'll label them just as we did before: S0, S1, S2, and S3. And so now this is the table from lecture 24, so I need to erase this information and to modify the column for Z. Here's X equals 0, X equals 1. And I guess we can go ahead and fill in the output columns. So we have 0, 1, 0, 0, and 1, 0, 1, 1. And now we need to simply fill in the next state in each one of these cases. 0, 0 is the S0 state. 0, 1 is the S1 state. Again, 0, 1 is S1. 1, 1 is S3. 1, 0 is S2. 0, 1 is S1. 1, 1 is S3. And 0, 0 is S0. And that state table should have all the information we need to analyze how this sequential circuit works. So now we will draw our state graph for this problem. And now things will look a little different from the way they did before, because this is, after all, a Mealy machine rather than a Moore machine. So let's get rid of this. And now let's see what happens. So according to our state table up here, if we are initially in S0 and X is equal to 0, then we will go to S0. So we can designate that in this way. But notice now that you recall in the Moore machine, the output depended simply on the state. And so in the Moore machine, we would put the value of the output here inside the circle along with the designation for the state. However, in a Mealy machine, such as the one we have here, the output depends on the input and the state, and therefore what we'll do is for each one of these arrows, it will have information not only about the input but also the output. So when we're in S0 and our input X is equal to 0, we go to S0 and we output a 0. So we'll designate that in this way. We'll say 0/0. The top 0 means that the input is 0, and the bottom 0 means that the output will be 0. Okay, now if we're in S0 and X is equal to 1, then we go to S1 and we output a 1. So we'll show that in this way. Here we'll draw an arrow from S0 to S1 and we'll say 1/1. And that means that when we have an input of 1, the top 1 means when we have an input of 1, and the bottom says we'll have an output of 1. Okay, now that you've seen that example, I suggest that you stop the video and try to fill in the rest of the state graph, and then resume with the video and check your work. Okay, so hopefully that went well for you, but we'll go ahead and finish it up now. So if we're in S1 and x is equal to 0, we'll stay in S1. So we could show that in this way. And what will we output if we're in S1 and x is equal to 0? We'll output a 1. And this should be 0 here. So again, this upper number is the input. So the input of 0 will send us back to S1, and the output will be 1. Okay, here you see the input is 0, sends us back to S1, and the output is 1. Okay? Now, on the other hand, if we're in S1 and the input is 1, we'll go to S3. So we could show that in this way. If the input is 1, we will go to 3. And the output, in that case, will be 0. Now, what if we're in S2? If we're in S2 and x is equal to 0, we'll stay in S2. And what will we output if we're in S2 and x is equal to 0? We'll output a 0. On the other hand, if we're in S2 and the input x is equal to 1, we'll go to S1. And in that case, if we're in S2 and x is equal to 1, we'll output a 1. And then finally, if we're in S3 and x is equal to 0, we'll stay in S3. And in that case, with the input of 0, the output would be 0. But if we're in S3 and we have an input of x equals 1, we'll go to S0. And the output in that case would be 1. And that is the conclusion of this state graph. Now, once again, if you're trying to follow along in your book labels the states differently, so the state graph will look different. But that's okay. The circuits will work in the same way. And so, as a final note about this sequential circuit, just as we did with our last sequential circuit, we will give an input sequence of x's, and we will suppose that, so here's our input sequence of x's, and we will assume that we are initially in the 0, 0 state, and then we'll try to predict what z would be. So remember now, 0, 0 is the S0 state. So if we're in the S0 state and our input is 1, then our output, the output will be 1, and we'll go to S1. Now S1 is 0, 1, so we can say 0, 1, and the output here will be 1. Okay, now if we're in the 0, 1 state, which is S1, and the input is 1, what happens? Well, if we're in S1 and we get a 1 input, we will output a 0, as we can see right here. If we're in S1, we get an input of 1, we'll output a 0, and we'll go to S3, which is the 1, 1, 1, 1 state. Now, if we're in S3, as we are here, and we get an input of 0, well, notice that, in fact, in every state, if we get an input of 0, we will stay in the same state. So, if we're in this S3 state, and we get this input of 0, we're going to stay in the S3 state, so we'll still have 1, 1. And notice that the output, if we're in S3 and the input is 0, the output will also be 0. Now, in the next step, we're in the 1, 1 state, S3, but in this case our input is 1, and so the state graph tells us that if we're in S3 and the input is 1, the output will be 1, and we go to S0. So the output will be 1, and we go to S0, which is the 0, 0 state. Now, if we're in the 0, 0 state, and our input is 0, remember, whenever we have an input of 0, we stay in the same state. So that means we'll have 0, 0. And for S0, if you get an input of 0, the output will be 0. And note that at the next step, exactly the same situation is going on. We're in the 0, 0 state, and we get a 0 input, so the next state will be 0, 0, and the output will be 0. Now in this next step, we're in the 0, 0 state, but we get an input of 1, and so the state graph tells us that in that case, we'll go to S1, which is 0, 1, and also we will output a 1. Now, if we're in the S1 state, as we are here, and we get an input of 0, we'll stay in the S1 state, so that's 0, 1. And we will output a 1 as shown right here. Here's S1, input of 0 will give us an output of 1. And then finally, if we're in the 0, 1 state, S1, and we get an input of 1, then that takes us over here to S3, which is 1, 1, and we output a 0. And we can't say any more after that because this is the last input about which we have information. So what this analysis tells us is that if we have the input sequence 1, 1, 0, 1, 0, 0, 1, 0, 1, and the sequential circuit was originally in the 0, 0 state, then our output sequence will be 1, 0, 0, 1, 0, 0, 1, 1, 0. And that's the way that we analyze a Mealy circuit. So now our our test problems for this lecture. It'll be similar to what we did in the last lecture. We're going to have a transition table, and looks like this did not copy over well, so I'll stop the video for just a moment to fill this in for you, and then we'll talk about these test problems. So now for the test problems for lecture 25. This is, as I said earlier, this is very similar to the situation we had in lecture 24. I'm giving you a transition table here that has A and B, and it gives you the output Z in all cases, and it gives you the next value of A and the next value of B in 3 cases, but in some other cases it leaves those values as unknowns, and you are to use this table or refer to this table for all of the problems for this test. And the circuit that you'll be using this time is exactly the same as this circuit here that we looked at in this lecture, with the only difference being that we have X prime here for JB input and X prime for the KA input. Otherwise, everything else will be exactly the same. And that is summarized down here. That's stated here as well. It says, for all of the questions, assume that we have the same circuit as above, except that KA is equal to X prime and JB is equal to X prime. So, since KA and JB are different, of course, then KA is different, JB is different, so that means that your excitation equations are getting changed. Now your output equation is not changed, and therefore the output will be the same as in the lecture. But since KA and JB are changed, that's going to change some of these values in the excitation table, which will in turn change some of the values in the transition table. And that's what you want to look at is you're interested in finding the new transition table for this new problem. And again, I've given you 3 of the values, but you will want to find in problem 25.1, you'll want to find alpha. In problem 25.2, you will want to find beta. And then in 25.3, that will be done in class. And that concludes the test for lecture 25. So good luck.